Today we're going to look at reaction mechanisms where you are given elementary steps with relative rate or rate that they don't tell you. And this is called the steady state approximation, where we will have to go through a series of steps to find out whether the overall reaction order of a given problem matches the proposed elementary steps. So in this video, we'll go through the mechanisms. There's no calculations, but it's just the steps that we're going to go through because there's quite a few steps. So first of all, we're given two elementary steps. The question will ask, find if this proposed elementary steps matches with the proposed rate law. Okay, but right now let's just put that aside and figure out how we could go about this. So in green, I've written the rate laws for the elementary steps. Okay, so, and then usually for reaction mechanisms, we would say that the rate of the overall is equal to the rate determining step, which is the slowest elementary step. But here, both of these are fast, or both of these are slow, or they just simply don't have the information that we need. So what we need to do is to use this, and I got the rate law. We don't know the order yet. And I got this by just canceling out the intermediates. So that will give us the general rate law with unknown orders. And then we want to use a slow rate determining step, but we don't know which one is slower. So in that case, if we don't know, just use the rate law of where products are formed. So that's usually the last elementary step. So I would just use the rate law of the last elementary step. Okay. So the problem with this is anytime that our rate law here includes an intermediate, we don't want that. This is an intermediate, which is something that is created in one step and consumed later on, so it does not appear in the overall reaction. We don't want any intermediates in our rate law, because if this intermediate was NO, then we could figure out what M would be equal to, because it would just match, but this intermediate is in the way, so we gotta do something. We're gonna apply the steady state assumption, where the rate of formation of the intermediate is equal to the rate of consumption of the intermediate. So then, the rate of formation of this intermediate would be the forward reaction of this first step. Okay? So this would be the rate law for the formation of this intermediate. And then we also want the rate of consumption of this intermediate. So this intermediate is consumed in two steps. The first step is pretty obvious, which is a second elementary step where it is part of a reactant, so it's being consumed to give a product. And then we also have to add the other place where our intermediate is being consumed, which is in the first elementary step with this equilibrium going on. That means in the reverse direction, N2O2 is also being consumed. So we would add these two rates of consumption together. And notice how I used -1 here. So that just symbolizes the reverse reaction of the first step, while K1 is the forward reaction of the first step. Okay. Next, hang on, rate of formation, rate of consumption. Okay, so this was not pasted correctly. Rate of consumption is this one. There. So we should be good now. Okay, let's just double check. The rate of formation is a forward reaction. Yep. And the rate of consumption is a reverse reaction. Yep. And also the consumption of the second equation. Perfect. So the problem with this is, we want to find something to substitute this intermediate. So we have to isolate for the intermediates in here. What we're going to do is, first we're going to factor out these intermediates. So on the right hand side, it's going to look like and then on the left, it's still the same thing. And the next step, after having factored out our intermediate, is we're going to isolate this intermediate. So we're going to put the intermediate on it one side. And this is from the left hand of the equation divided by this. Now, the problem with our thing here is that when we put it into this, it's going to look really complicated. So I'll show you what I mean. I'm just going to copy this in. And then for our N2O2, this is our expression for N2O2. And then our O2 is still outside here. Okay, so we don't like having so many K's under here because it doesn't clearly tell us what is the reaction order. So there is still a step, and that is applying restrictions and applying limiting factors. So these limiting factors are what we call extreme conditions. So the situation might look something like this. We know that K -1 is the reverse direction of our first elementary step. And K2 is the forward direction of our rate of consumption for the intermediate. So we don't like these two things. We have to get rid of one, and this is what we call the pseudo reaction order, where we combine the two K's. And which K do we combine? Well, in that scenario that you're given, whatever the question be, if you get the implication that the rate of the reverse direction of the first elementary step is greater than the rate of consumption of the second elementary step. So to rephrase, if N2O2 is consumed faster in rate 1 than it is consumed in rate 2, then we could combine K2 and K -1 into 1K. So what that means is for this denominator, we can simplify it. So if it's in the first case, instead of writing all of this long boxed thingamajig, we can just say that K1, K negative 1 plus K2 is pretty much just the equivalent of K negative 1. So instead of writing all this fancy stuff, we can just write K equals negative 1 in the denominator. So let's model that. So this would become something like K2 K1 and then this is our K minus 1. Okay, what about the second restriction? So the idea is that if the rate of the second elementary step, if the rate of consumption in the second elementary step is greater than the rate of consumption in the first elementary step, then we could basically combine K negative 1 into K2. So instead of writing all of this, we would just say, well, if we really do add K negative 1 plus K2 with oxygen, it would just be the same, pretty much the same as K2 and oxygen here. So then in application, that would make our overall equation look something like this. So our K1 is still on top, no, is still on top, and oxygen is still on the top, but at the bottom is what changes. And then we can also simplify it by canceling out a few things. Okay, so these O2 cancel out, and these K2 also cancel out. So then what you're left with is just this incredibly simple equation, which is great. And just one last thing to do with our first thingamajig that we need to finish off first. We would also combine the K's so that it looks like this. So then, instead of writing this fancy denominator thing here, we would put in our simplified form. So we would put this, and then we would put in our NO2 and O2. So that instead of this complex equation, we would put in this instead, or this instead, in the place of this. So that when we bring our overall rate law down here, we will be able to compare whether their reaction orders are the same or whether it's different, how different it is, and overall find out whether the reaction orders match, so that this reaction mechanism can be confirmed or to be refuted.